Welcome. In this session on finding a minimizer of a function that has a scalar argument, we'll explore how we can automatically calculate a variable step size given a first guess at the step size that the user provides us. So the concept that we have is based on the idea that the user's step size may be too large. So let's note that if S is too large, then what we saw previously was we can get this kind of behavior. We could get, so for our little dynamical system, what we saw was if this was our T1, we had a T2 that was too large. And in particular with that example, what we saw was that T2 was so large that the value of the function at the new estimate was higher than the level at the original estimate. So let's consider reducing the user's step size. Now, this could be quite complicated because we don't know very much about the function. All we know is when we evaluate it, we get a certain level. And we really don't know very much about the, for example, the sheer magnitude. Are these in millimeters? Are these in kilometers? We don't know what measurement system these are taken from. So we have very, very little information. And what we do know, however, is that when we took the step S, it was too big. That's the one thing we're sure. So what if we tried to back off? So let's put that in quotes. Let's back off S using a sequence. So what we could try is we could try S. And then we could try, for example, we might try taking half a step and 1/4 of a step and so on. So this is using some value of beta. So beta is the backing off rate, or sometimes called the backtrack rate. And what we want is we want beta to be strictly greater than 0 so that we're doing something, and we want beta to be strictly less than 1 so that we're getting this exponential reduction. So what that is, what we're doing here is we're creating a sequence. So our sequence is, this would be S, and then beta times S, and then beta squared times S, and so on. Or we could write that as beta to some index value gamma times S. So this would give us a way that we could back off S, and this would be an exponential back off. So what we would do is here, if the initial S was too large, we would say, oh, the function value here is greater than the function value here, so we don't want that. And let's try going halfway. And if we went halfway, we would see that the function value here is less than the function value there. And if we're near a local minimizer, that's a good thing because it's getting us closer towards that minimizer. So what we can do is we can compare, and we can loop while. And now let's write down a mathematical comparison for what we're doing. What we're saying is that if we take a step, so we start at k, and if we take a step in direction d, that is the user's s, and now what we're doing is we're multiplying that repeatedly by gamma. What we want is when we evaluate the function at that new point, we want it to be less than, or sorry, since this is a while, since I stated this as a while problem, what we want is this to be greater than or equal to the function evaluated at our current estimate. So if we do this loop, then eventually we'll get to a place where this condition is satisfied. Now, let's think ahead. This will work, but it may not work as well as some alternatives. So let's consider what line is being tested. And what I mean by that is, suppose we have our function, which is locally convex here, and suppose that this is our current estimate, which is tk. What we're saying is we want a new tk plus 1 that evaluates to be less than that. So what we're doing is we require that f at tk plus 1 is below, and here I'm putting it in quotes because it's a geometrical statement, is below the line. And now I can write that line as a function of t, and that is f of tk plus, well, this looks a little odd because it's 0 times our t. So that is the line, is that it's a line with a constant value. Now, is there a better way to select this? So where we've come is that our exponential back-off sequence, what we're doing is we're going to continue backing off until we get an improvement in the function. And the question for the next session is, can we do better than that? Can we have a better comparison than comes from this exponential back-off?